waiting for anybody else. So our speaker today is Richard Ehrenborg, and he will be talking to us about the topology of restricted partition posets.
Thanks so much, Jeremy. So this talk is unrelated to anything else that happened this seminar so far. So it's joint work with my grad student, Yi Young. So let's begin with set partitions. So a set partition is that I take a finite set, usually it's the set 1 for n, and I divide it into blocks. Non-empty blocks to be disjoint would union the whole thing. So if you look at the filament set containing 1, 2, 3, there are going to be 5 set partitions. Namely, 1 is a singleton and 2, 3 as a pair. 2 is a singleton, 1, 3 is a pair. 3 is a singleton, 1, 2 is a pair. Or find the last one where each element 1, 2, 3 are all singletons. So these are the 5 set partitions of 3 elements. And there's a natural partial order here by you going up in the poset by taking 2 blocks and joining them. So this is the minimal element, and everything in 1 block here is the maximal element. So this is the partition poset on 3 element, pi 3.
It's a ranked poset, I guess.
Yeah, it is ranked poset, the rank being something like n minus 1 minus number of blocks, something like that, if I did it right. Okay. So let's now look at
The ordering is ordered down. Yes?
yeah, the ordering is you take 2 blocks and go up. If I join 1 and 2,
That's the minimal element.
yeah.
Okay.
So now let's look at this poset. It's going to be all partitions where each block size is even, i.e. each block size is divisible by 2. That's my index there. So if we draw it, pi 4, 2, I have the maximum block, everything in 1 block, and 4 is even. I can have 1, 2, 3, 4. I can have 1, 3, 3, 4, and 1, 4, 2, 3. And that's all I can have. That's all the partitions on 4 elements where all the block sizes are even. Now it's a theorem. By Sylvester. No, it's not the Sylvester you're thinking about. This was in a physics dissertation 1976 at MIT. Yeah, much later. And he proved that the Mobius function, if I take this poset and I had to throw in a new minimal element, is given by minus 1 to the n times the n minus first Euler number. So the Euler number for us is number of permutations in the symmetric group on n elements that are alternating, i.e. the first element is less than the second, which is greater than the third, which is less than fourth, and so on. Permutation having this pattern. So
Wait, that's the Mobius function applied to, let's see, the guy on the right is a number, the guy on the left is what, a function? Or
yeah, well,
you've applied it to it?
Well, I think it's a Mobius function of a poset is really the reduced Euler heuristic
So
No.
this is the Mobius function evaluated in the top element
Yeah.
of the poset.
Yeah, between top and bottom here.
Yeah, right.
And that's why I had to free in the new bottom element.
I see.
And for your topologists, you can think about the Mobius function as I take the order complex of the poset, throwing away top and bottom elements. The order complex is just a set of all the chains that form a simplicial complex. And I'm looking then at the Euler characteristic of that. So it's very concrete about it. That's not the way you define Mobius function in combinatorics, but it's good enough. Yeah.
So what is it here for pi?
Yeah, so here you're going to get the Mobius function 2. Because we add in the new minimal element. And then I look at all the chains.
Calderbank is -1, right?
So the other
Yeah, this is just going to be 3 points.
Oh.
So the result is 2.
Okay.
Yeah. Yeah. And that corresponds to here n equal to 4 as we look at E3. E3 is 2 because I have the permutations 1, 3, 2 and 2, 3, 1. So all the permutations that has that pattern.
Pi in, what is that?
Okay, number of permutations in the symmetric group such the elements are alternating. Yeah. Another way to think about En,
pi sub 1 is the image of 1 in the
Yeah. Yeah, I think about pi in one line notation. Yeah. And the Euler number you all know, because you have seen it. If you put it into generated function, this is just tangent x plus secant x. So in fact, you know tangent here is not function, secant is an even function. And for this result to make sense, n has to be even. Otherwise you can't take an odd number of elements divided up into block of size even. So that means I'm looking here en minus 1, that means the index is odd. So these numbers appearing here are also known as the tangent numbers.
I mean, because the secant, you can drop it out. Well,
Yeah, because I'm only interested at the moment in the odd index things here. So now, Sylvester's dissertation on his dissertation committee was Richard Stanley, who said, oh, this is interesting. This has a natural generalization. That's what happened. Namely, let pi dn be all partitions of the set 1 for n, where each block size is divisible by d. So far we looked at pi n index 2, and then m due to Stanley is that the Mobius function, if I look at these partitions, I have to throw in a new minimal element. So compute the Mobius function from the top and bottom. This is minus 1 to the n over d, that's just the sign, times number of permutations, and I'm thinking of it still in one line notation, such that pi of 1 is less than pi of d, so it's increasing in the first positions, but at pi of d I have a descent, I go down, and then it's increasing again Oh, I lied. It's a -1 here at the moment. And then I go up to pi 2d, and then I go down. So at every diff position, the permutation go down all the way to pi n minus 1 here. So it looks like I go up, down, I go up, and then down, and it continues this pattern. So here's an example for n equal to 9. So notice I'm going to be just on permutation in the symmetric group of n minus 1 elements, and d is equal to 3. So in every diff position, we have a descent. Which nicely generalizes the result by Sylvester. Then the next result, 3m due to Michel Wachs. And it says that the poset, the d-divisible partition lattice, free numeral, is Ehrenborg. So Ehrenborg is a condition on the poset such that you label the edges of the poset so that it gives actually natural shelling of the order complex. So let's not go into that. Let's go and put the corollary I want after this. Corollary, the order complex when I take this poset and I remove the top element, which I had to remove because otherwise the order complex would be contractible and have no interesting topology, is homotopy equivalent to a wedge of, well, that many spheres
What does the EL stand for?
edge lexicographic.
Yeah.
It stands for edge lexicographic, and is a condition to how to build up the complex. But what I really want to concentrate is the corollary. That many spheres of dimension n over d minus 2. So this is really,
All of them the same dimension. This
yeah.
Because you're looking at the.
Yeah, it's nice and graded. You can all the same dimension. And there's really extends which is standard result about the Mobius function, because when you take the reduced Euler heuristic here, you pick up exactly the number of spheres, which it gives about this thing. Then the next part in the story is, notice that I have these constant permutations on n minus 1 elements. So the symmetric group Sn minus 1 acts on this poset. Well, that means that the symmetric group acts on this order complex. Well, then means that the symmetric group acts on the reduced homology nd minus 2, the top homology group. And theorem by Calderbank Hanlon and Robinson is that this action is the Specht model of shape
What is the delta is the invariant? What is the-
Oh, delta is the order complex.
I know that, but the tilde on the
Oh, the
equivariant
no, reduced homology.
or reduced only 8 zeros.
Yeah. But if I put in reducing, I don't have to worry about H0 case. The Specht model of shape, I'll just draw it over here. It's going to be the shape where I have D boxes at the bottom. D boxes is next row. And this pattern continues with D boxes. Okay, I'm going to draw it slightly compressed, running a blackboard, so that's D boxes in each row, except that in the last row, I have D minus 1 boxes.
Are you going to remind us what a Specht module is?
No, I'm not going to remind you. I'm going to use that. Well,
Okay.
it's a little bit complicated to put up in a minute. But it's just that the action is well defined. It's known as something previous object. And furthermore, the dimension of a Specht model you will get by you fill in the numbers 1 through n minus 1 into these boxes, such that each column is increasing, each row is increasing, and that gives you the dimension of the Specht model. And now you see that that's actually exactly the same number as a permutation this way. Because if you take this picture and I flip it so this the box is going this way, then you see I have the numbers increasing and then a decrease, increasing, decrease, decrease. So it's this thing is very natural in comparison with the descent pattern going this way. However, the strange thing here is all this result is that this number of permutations on n minus 1 elements. I'm working with partitions of the elements 1 for n, and for some reason I had to drop the n last element n element. And for the group n minus 1 elements, here the same thing, I have n minus 1 boxes here. The action was by the symmetric group n minus 1 elements. So first, in order to get forward, we had to explain that away. What happened to the element n? And one way to look at it is I'll take the hyperplane arrangement xi equal to xj.
So you're saying this homology group is a module over sigma n?
Yeah, this is
And this just gives part of the structure.
yeah.
This Specht is in the homology, this action.
Yeah, the symmetric group acts on this thing, and this action is isomorphic to the Specht model. The Specht model is in representation of the group Sn minus 1.
Right. But Snx, the full symmetric group on n letters x.
Yeah, that's true.
Right. So
So there's more structure in there.
there's more structure that this doesn't reveal.
Yeah.
Yeah.
So I take the hyperplane range with all xi equal to xj for I less than j less equal to n. So that takes place up in n-dimensional space. This is a typical AN arrangement. And just to quickly draw it, I'll do it in 3-dimensional space. I have these 3 hyperplanes meeting in one line. But now, you realize that since this contains the line here of all the coordinates equal, this is not an essential arrangement because all the this 1 degree of freedom in it. So the natural thing would be take this thing and cut it with one hyperplane like this and bring down dimension by 1. And the way we do that would be that we cut it with xn equal to 0 So the same arrangement, xi equal to xj, 1 less than j less than minus 1, and then with xi equal to 0. And yeah, so picture is like that now. And it contains the same combinatorial information. But now, it differs slightly in the representation of understanding this, because how does look in the intersection lattice here? How does an intersection look like? Well, when I set two blocks equal here, if I start setting coordinates equal, if I put x1 equal to x2, x2 equal to x4, then you know that x1 is also equal to x4 by transitivity. So the intersection lattice here is the partition poset. Namely, if I had the block 2, 3, and 5, that means I should set x2 equal to x3, x3 equal to x5, and x2 equal to x5. But now, look at the intersection lattice over here in this picture. We have a different way to look at it. Namely, now it really looks like a pair pi z, where z is just a subset of 0 to n minus 1. Namely, these are going to be the corresponding coordinates which are going to be set to 0. And pi is just going to be now pi partition of the complement c bar. And this is still these are all the blocks with all the still non-zero coordinates. So looking at it this way, I get rid of my n. So now we're going to do this shift, and I could actually work, instead of working on partitions on n minus 1 elements, I'm going to work on n elements this way. And I'm going to call this a pointed set partition. So this is going to be denoted by Pn here. And when I'm going to work with these blocks, I'm going to have like the partition 1, 2, 3, 4, 5, 6, 7. I'm going to underline the pointed block. So before in the partition, the order within blocks doesn't matter. Now, the order doesn't matter except that the pointed block is always pointed. And I'm always going to draw this to be last. And as before, this is a poset structure on these things. I go up by joining two blocks. And if I join with the pointed block, like I can get 3, 4, then that's going to be the pointed block. So this is not really a new structure. This really is isomorphic to the partition lattice on n plus 1. Because I didn't really, when I intersected with this hyperplane x n equal to 0, I didn't do anything new. I just had the same combinatorial structure. But you see the bijection here by taking the element, taking this pointed set partition here. I take the 0 block, the pointed block, and I drop the element n plus 1 into it, and then I let it be unpointed. And since I know n plus 1 is in it, I can go backwards by taking the block n plus 1, removing n plus 1 from that block, and I get the pointed block. And then I point it. So this is one of the structures I'm going to have to work with. Other thing we're going to need just one more detail. The 0 block could be empty. So that slightly is different from an ordinary block also. Whereas other blocks have to be non-empty. The other structure I'm going to see, I'm going to need composition of n. And that just means I'm going to have the sum of these entries in this vector. It's going to be n. And I'm going to need all the first entries except the last one to be going to be positive integers. And whereas I can let the last thing actually be a 0. And this really corresponds to that I can have an empty block as a 0 block. But don't let this last condition bother you. But the compositions, as usual, forms a partial ordered set. I can take two adjacent entries, I can add them together and form a new entry. So if you look at everything, I start with the composition 1, 1, 1. I can either add the two first ones, I get 2, 1, 1, 1. I can add the two middle ones. I can make the last two ones. I can have 3, 1, adding the two first here or the two first here. I can obtain 2, 2, here, here, 1, 3, and then finally 4, composition into one part. So you see this is natural partial order. And you realize I haven't done anything new. This is really the Boolean algebra on 3 elements. And this natural projection that proves that. Finally, we had to come back and start talking about permutations again. So I'm going to find beta of a composition. It's going to be number of permutations pi in the symmetric group of n elements with descent pattern. And let me use, instead of trying to write it down, it's easy to draw a picture. So this is the pattern of permutation. This is going to be C1, this is C2, C3, and C4. So this is really the composition 3, 4, 1, 3. You just count how many elements are is increasing sequence in the permutation. So the quantity in Stanley's theorem, in Michel-Wachs' theorem, and so on, is just the quantity beta of the composition d, d, all the way to d, and the last entry being d minus 1. Finally, one last structure to play with. Oh, maybe I should use that board.
Do you have an efficient way to count these permutations, like the secant plus tangent?
Well, there's nothing as beautiful as that generating function, but there are efficient way, like this known as V0 triangle, that actually quickly computes them by adding things up. It's something very Pascal-looking triangle. And sometimes it's easy to do it when you have few parts in the composition. You can use inclusion and exclusion from multinomial coefficients. So depending where you are, there are different techniques for it. So last thing I'm going to need is I'm going to have, well, we have integer set partitions. Well, there are set partitions, and now I'm going to need integer partitions. And I'm just going to think about an integer partition as a multiset of positive integers whose sum is n, i.e. that's a integer partition of 5, because 3 plus 1 plus 1 is 5. However,
Multiset just means you can have something twice.
yeah, I can just repeat integers. However, notice I'm working here with pointed set partitions. So I should also introduce the real notion I need is pointed integer partitions. And that's just going to be that I'm going to have this partition 3, 1, 1, 1, and 2, and I'm going to have one part is pointed, one part is special. Now, we can putting these structures together. So over here, I'm going to pointed set partitions. Here, I want to have pointed integer partitions. Well, it is a natural map going here. Namely, I have a pointed set partition. I can use read off the cardinalities of each block. And I'm just going to make it easy for myself and call this the type of a pointed set partition. Similarly, I can take a composition of n, and I can just, taking here, I can start permuting the elements, and I will get an integer partition of that. Not caring about the order. However, I don't want to have an integer partition. I would like to have a pointed integer partition. So I'm always going to keep the last part as the pointed part over here. So the last element of the composition is going to be the pointed part here. And just to make it easier for ourselves, and call this the type. So now I can define the structure that allows me to generalize this theorem of Stanley, Wachs, and also Calderbank, Hanlon, and Robinson. So C is a composition, and define pi pointed of C to be all pointed set partitions on n elements, such that there exists a composition D greater than C in the partial order of the compositions. So the type of D is the type of pi. So notice that one of these types I'm using here is of composition, the other type I use pointed set partitions. By combining this thing, so note, for instance, if I work with C equal to composition, all the parts equal d except the last one, then pi of c in this case is going to be the d-divisible partition lattice. Because what happens when you go up from this composition, well, when you add adjacent entries, all the thing happening in the front here is going to be divisible by d, except for the last part is always going to be congruent to -1 modulus d. So you can have any. So that means when I'm looking at this possible integral combination, it means that all the parts are divisible by d except for the pointed part has to be going to -1 mod d. But that's exactly what I get in the d-divisible partition lattice, where I remove, well, I'm sorry, it should be an n plus 1 there. I remove n plus 1 there. That block is going to have size congruent to d minus 1 mod d. So this is the right analog going up, and the result is theorem. First of all, the Mobius function is the right thing. This is -1 to the k times beta of c. C being my composition. If I, well, okay, actually, really, add in a new minimal element there. If I look at the order complex, I can remove the top element, then this is homotopy equivalent to the wedge of beta c spheres of dimension k minus 2. So the topology, the homotopy type, is the right thing of this thing. Unfortunately, where I don't have is a shellability result for this complex. But I had the topology, so I have the homotopy type, so that's good enough. And finally, we know that I have spheres dimension k minus 2, so the only reduced homology happens here dimension k minus 2. So then I can look at the reduced homology k minus 2 of this order complex. And this is isomorphic as an SN module to the right Specht module. The Specht module shape, and I'm going to have the same border strip Specht module. We have C1 boxes in the first row, C2 boxes in the next, C3 all the way up, the CK boxes in the last one. So all the results are there except for the shareability result.
Am I right in my picture of this that when you have this simplicial complex, the symmetric group acts on it, and the quotient space is just a single simplex? Is that? And I mean, I would like to see some sort of local description of this complex, like if the quotient space was a simplex, just what the stabilizer of each face was, or if it's not that, what the link of a vertex is.
I don't know how that looks like, because I'm really are permuting the elements inside each block, so I don't. The stable.
Aren't all the top simplices equivalent under the symmetric, or am I wrong about that?
I don't think they are equivalent. They could be different. But we can think more about that later. So,
How do you prove it's a homotopy of wedge of spheres without shellability?
okay, that's what we do now. Good. So, so I need one more structure in order to make this work. So I'm going to need ordered set partitions. So in a partition, there's no order between the elements. So the partition 2, 1 with the same partitions 1, 2. Now I need an ordered set partition, which means that I actually going to keep everything in order. So if I change 2 blocks here, I'm going to get a different ordered set partition. And yet again, how do I go up? They form a poset. And what's the correlation? Well, I'm always going to join 2 adjacent blocks to go up. So it gives me, in this thing, over here I have ordered set partitions. And if an ordered set partition, it's natural to, well, I can just read off the size of the blocks and I get a composition. Or if I start permuting all the blocks except the last one, because the last one is going to be the pointed block in the partition here, then I get a natural map going there. So it completes this diagram in the right way. However, let's look at this order I have here and what happens with it. Well, if I have an ordered set partition A, B, C, I have 3 blocks. The only way to go up in this poset, well, I either have to join the 2 first ones or the second 2 ones, or then here. So you realize that when I go up, it's just going to be like a Boolean algebra. Just as it was with the compositions. I mean, you see actually the actual natural bijection here between here and the Boolean algebra, replacing either you have a comma or a union sign, agree? They're just like 0, 1, being in the set or not being in the set. So ordered set partitions, as an interval in a poset that is very boring, use a Boolean algebra. However, other things can happen. So C composition, I'm going to let delta C be the set of all ordered set partitions sigma. So the type of sigma, and I'm meaning that type, is going to be greater or equal than C. But I'm going to view this as a simplicial complex. So let's do an example of this so we can read it so nice and draw. Okay, so if I take 1, 2, 1 as my example, going up from that, I'm going to have 3, 1, 1, 3, and 4. So C is equal to 1, 2, 1. So let's look. 4. there's only one set partition of that type. So the number of such things could be 1, and this is going to be the empty set or empty phase of my simplicial complex. Then I have phi 1. Well, I have 4 elements. I should put the first 3 down and the next one. There's 4 ways to do that. There's 4 ways to choose which element should go here. Or I can have 1 3, which is also 4. So these two are going to be my vertices. So in this example, I'm going to have 8 vertices. And then we have to look at the composition C itself, 1 to 1. Well, I have 4 ways to pick this element. Then I have 3 ways to pick this element. And the remaining 2 I had to put in the block in the middle. 4 times 3 is 12. And this is going to be my 12 edges. So here I'm going to have a graph. My vertices and edges. And what a graph, do you know, has 8 vertices and 12 edges?
One skeleton of a cube.
Yeah, one skeleton of a cube. So I have to draw it. And nicely label it so you can see this thing. So now, this example, be careful I don't screw up. So here is going to be the ordered set partition 1, 2, 3, 4. Then, if I join the 2 things together, before I was going up, but in my simplicial complex I had to turn things around, so then I'm going down by joining a base and block. So this is my vertex 1, 2, 3, 4. My empty phase is 1, 2, 3, 4, but being topologist, you can't see that, okay? Then over here, we have 1, join 2, 3, 4. Here I can have the edge 1, 2, 4, 3. Still joining here, I get here. Or I can go the other way. I can have to go to the vertex 1, 2, 4, join 3. Here I have the edge 2, 1, 4, 3. Then here, then joining the 2 first ones, I go here. Then the last one here, I get 2, 1, 4, 3. And this edge here is a 2, 1, 3, 4. And now let me just not mark the rest of the vertices. Let me mark the rest of the edges. 3, 1, 4, 2, 3, 2, 4, 1, 4, 1, 3, 2, 4, 2, 3, 1, 2, 3, 4, 1, 4, 1, 2, 3, 1, 3, 4, 2, and 3, 1, 2, 4. So this is a nice simplicial complex. Well, topologically, so here's lemma. This simplicial complex is homotopy equivalent to a wedge of beta C spheres of dimension k minus 2. So, and you can see that if beta C should contain permutations, and let me mark out these ones. If you look at this thing and you read this as a permutation, 4, 1, 3, 2, you notice I have descent here and descent here. The same thing here, I have descent, descent, reading as a permutation. Here I have descent, descent. Here I can have descent, descent. And finally this one, descent, descent. And in fact, these are all the ones that have that descent. So beta 1 to 1 is indeed 5. And if I look at the remaining things, these are all going to be facets in the Symmetric complex. And now on the remainder, I can easily find a discrete Morse matching. So that if I remove this thing, these 5 things, the rest is going to be contractible. And the discrete Morse matching is very natural. This is 2, 1, 3, 4. Namely, you can read, and so you can match, you read along. Is this right? No, because it's wrong. Dash 2. You read along here, and you realize that I should match this with this one, because that's the first time I can actually go in and put in and dash in here and get this edge. So you can actually match the rest of the faces together, so there's no creating new acyclic cycles. And in fact, this actually is corollary for something by Björner and Stanley on EL shellings of the Boolean algebra. So it's actually a very natural thing. So what I can prove, now coming back to Bob's question, how do we prove something like this? Well, there's Quillen's fiber lemma, which says the following: if I have a simplicial map phi from simplicial complex gamma to poset P. So this means it takes elements here to takes vertices here to elements in the poset, and it takes faces into chains, and here comes into condition that for all poset elements here, if I look at everything greater than an element x, and I take the inverse image of this, yeah, so if for all x this thing is contractible, then the simplicial complex gamma is homotopy equivalent to the order complex of the poset P. Quillen proved this thing. And now we can apply that by going between starting here, and we really go then to ordered set partitions. So we actually, instead of looking at this pi dot c that I'm interested in, I start looking at ordered set partitions. With, of course, introducing ordered bundle blocks is going to make it much bigger. But then Quillen's fiber lemma proves it's going to be the same thing. But however, what I'm looking over here at ordered set partitions, that's really just going to be the pericentric subdivision of this complex. So I go for something rather big, there's something even bigger, which is a nice subdivision of this thing. And hence the result follows. And applying Quillen's fiber lemma here, it actually turns out that not only, I should stop soon, is that it is contractible, but it's elementary to prove it's contractible, because what comes out in this case is that this is actually is a cone over an element. So this application is actually very easy to do. So
And you put greater than x or greater than or equal to x?
let me check. Okay. I was unsure when I wrote it. No, actually greater or equal, you're right. Oh yeah, it should be greater than equal because it's not going to be cone over x. X has many images going backwards here. So that proves the topological result here, the homotopy equivalence. And then the SN model action, well, since the map phi I'm using is forget the order among the blocks here, that map preserves the SN action, and then I can show that the top homology groups are actually going to be isomorphic. And it's actually not too hard then to get that this one, S4 acts over here, and it's going to be the right Specht model. In this case, looking like one block, two blocks, and then one block. So that's all I had to say. Thank you much.